This is page 177 in your note guide, and we're going to hit this really fast. So let's look at differentiability and when f prime of a does not exist. So there are times when you cannot differentiate the function. One of those times is when you have a corner. So if you have y equals the absolute value of x, and I asked you to find the derivative. So just a reminder, this is what the absolute value of x looks like, kind of. And as I'm approaching 0 from the left and the right, I want to know what the derivative is. Well, the reason why this doesn't work is because I could find the slope of that line, but I could find the slope, oh, that one didn't work. I could find the slope of this line, and you can see that the slopes are different. And because of that, there's not just one solution, and so there's no derivative for example 6. So no derivatives at corners of functions. Example number 7, y equals x raised to the 2/3. I just want to remind you that that's the same thing as y equals the cubed root of x squared. So if I look at that function, if you were to graph it on your calculator, it looks something like this and like this. And we call this area in the middle a cusp. And we can't differentiate because of the same reason as before, that I can draw a line going that way. It's supposed to hit the cusp. Let's try again. I can draw a line that way. I can draw a line this way. And so because of that, I can't differentiate. Okay, let's look at the next example. Example 8, y equals the cubed root of x. So just a reminder of what this graph looks like. If we have our graph, and I'm just trying to sketch these really quickly, but our cube root graph looks something like this. So we have this part and then this part like this. Okay, so there's our cubed root graph. And again, we have the same problem as I approach 0 from the left and right. There are different ways that I can draw that line, and so because of that, I can't differentiate because the slopes of those lines will be different. Looking at example 9. Example 9 is a piecewise function, and you're going to see this function quite often in calculus. So y equals 1 when x is less than or equal to 0. So that's going to be y equals 1 when I'm smaller. And then y equals -1 when I'm greater than 0. And this time it's an open space, and I'm going in that direction. So remember that as I approach from the left, the limit is going to be up here, but as I approach from the right, the limit's going to be down here. And because of that, the function jumps. And anytime the function jumps, you're not going to be able to differentiate. So there's no derivative for functions that jump. All right, the last problem is a you try problem. So you can go ahead and stop the video. You can try this problem on your own, and then you can come back and start the video and see if your answer was correct. I'm going to stop the video and work it out. So this is the definition of a derivative. This is the long way to work out this problem. So when you watch the short video, you're going to see a shortcut of how to do this problem, which is pretty amazing. But anyway, so I did the limit as h approaches 0 of f of x plus h minus f of x over h. And the whole reason that all year we've been practicing with this function is for this moment where we can use it to find the derivative. So I went ahead and everywhere I saw x, I plugged in x plus h, which gave me 1 over x plus h plus 4, subtract 1 over x plus h, because it's subtract f of x. This is f of x all over h. We are going to go ahead and get a common denominator in the numerator. I can't directly substitute because 0 would be in the bottom of the fraction. So this fraction I'm going to multiply, let's see, by x plus h plus 4, top and bottom, x plus h plus 4. And this fraction, I'm going to multiply the top and bottom by x plus 4. And I'm doing that because I want a common denominator. So now, when I have a common denominator, and let me scroll down, I really need more room. Okay, so, all right, so let's see what we have. X plus 4 times 1 is x plus 4. Subtract this whole thing. So this is negative 1 times this, which is negative x, subtract h, subtract 4. All over the common denominator, x plus 4, and we're not going to multiply out the denominator. That would be way too much work. X plus h plus 4, all over h. So what we're hoping for is things are going to cancel. So negative x and positive x cancel, 4 and negative 4 cancel. And so now what we're going to be able to do is this h will cancel with this h, giving me just negative 1 in the top. So the limit as h approaches 0 is going to be, see there's a negative there, so we're looking at negative 1 over x plus 4 times x plus h plus 4. Now I'm going to use direct substitution. Everywhere I see an h, I'm going to put in a 0. So this gives me x plus 4 times x plus 4. This h right here went to 0. So that's why I got x plus 4. Ooh, that doesn't look like x plus 4, does it? That's a 4 right there. Okay, now what we can do is we can find what the slope is at 0 and what the slope is at negative 2. We're not interested in the y values. We want to know the limit when x is 0 and when x is negative 2. And I said limit, but I meant we want to know what the slope is when x is 0 and what the slope is when x is negative 2. So I found the derivative. Here's the derivative. And I can figure out the actual slope by plugging in 0 first. So 0 plus 4 times 0 plus 4 is equal to negative 1 over 4 times 4 is 16. So there's the first slope. The second slope, you're just going to plug in a negative 2. So negative 1 over negative 2 plus 4 times negative 2 plus 4. Negative 2 plus 4 is 2. So this is 2 times 2. And 2 times 2 is 4. So the slope at point negative 2 and up a half is going to be negative 1/4. Okay, so now what you're going to do is watch the short how to find the derivative. It's pretty amazing.